So we're now at the point to consider these infinite limits. What this video is going to be about is explaining sort of the background, a little bit of the delta epsilon behind it. This is not what you're going to need to be able to reproduce or work a problem with. I want to show you what's actually happening with the deltas and the epsilons and what's happening with the picture, and then we'll actually get to the computations later on. So, what do we mean by this statement? Now, for one thing, this equals doesn't mean the same thing as equals used to mean, because it doesn't make sense for our work to say some quantity is equal to infinity. So we're modifying the equal symbol to mean the limit of this expression is represented by this symbol. And so this is a representation of a concept. It's not the same notion of equals that we talk about in ordinary mathematics in the finite realm. And so that's going to be from here on out for the rest of the course. I'm not going to say that every time, but from this point forward, anytime we have equals infinity, we are to understand that as meaning it's not equals in the ordinary finite sense. It is a representation of a concept that we are understanding. All right? In fact, the concept that we're hopefully understanding is the limit concept. This equals is representing a limit expression that we're going to talk about now. All right. Well, I've sort of already spilled the beans here. Consider this function. Consider a function that has a vertical asymptote at A in this fashion. Now, what do we mean when we write this expression? Well, a couple things. First off, this. Let's suppose this is true. Let's suppose we have established that this is a true statement. If this is a true statement, then this should be a false statement because this is a finite number. If this is a true statement, then this is a false statement. And that means that the deltas, epsilons don't work here. Now, why is that? Okay, here's why it doesn't work. Suppose it did. Something must go wrong. We know this is false. Okay, we're claiming this is a false statement. And so if we suppose it's true, something's going to have to go wrong. Something's got to fall off the rail. And here it is. Given any interval, epsilon interval around L. The question is, and what I'm claiming is it doesn't work. The question is, can we find an associated delta interval here? And what must be true? The function value of every single one, not just some, every one of these x values must have a function value that falls inside this blue interval. But you can see, even at the scale of this terribly drawn picture, you can see that's clearly false. Because if you get close enough to A, the function, for values out here, no problem. But if you get close enough to A, the function value recedes up the graph. The function value is way up here. That's what we mean by this vertical asymptote. These arrows, they indicate that this curve never returns back down. It continues to elevate without boundary. And no matter how small we choose, or no matter how large we choose epsilon, inside of here, there will eventually be numbers so close that the function values will be above that, even that value. What if we choose an epsilon that big? Well, no matter how big the epsilon we choose, we can find values that are close enough that they will recede up the graph and be above the value in question. And so this never happens in this scenario. So here's the way we word that in the language of the epsilons and the deltas. Actually, it turns out epsilon is no longer in play. What we say is this: in order for this to be true, pick any number on the y-axis. Pick any number. I don't care how far up the y-axis you pick. Pick any number on the y-axis. Depending on the scale, this might be 100. Depending on the scale, this might be 10. Depending on the scale, this might be 1,000. Depending on the scale, this might be a trillion, trillion, trillion. This could be any number on the y-axis. If this is true, if this really is a vertical asymptote, and if these curves really do recede off without boundary, then I don't care how, let's call this, we don't want to use the L, let's call this M. I don't care what M you pick. What always will happen is you can find a small interval around A. There's my delta and delta. So actually epsilon's gone the way of all flesh. There are no epsilons in this, but there is a delta. And what we're saying is, for every x value in that interval, every one of these function values is above m. Every one of these function values is above m. And I don't care how big of, you give me a big M, and I'll tell you how close you need to get above that value. If m is 100 million, then you get close enough, and these function values will be above it. So given any m, I don't care how large it is, given any m, that if you get close enough, but not equal to A, not equal to, when the limit, we don't care what happens at A, you can get close enough to A that every one of these function values is greater than m. Now, I'll write that out, and then we'll kind of leave this behind and get more to the sort of user-friendly version. It means this. For any m, for any value m, I don't care which one you pick, there exists a delta such that, and what must be true? What must be true? We said every x inside that interval except x equal to A. This is our same familiar. X is inside the interval. X is not equal to A. If this is true, that implies what must be true of these function values? The function values don't need to be inside of an interval. The function values just need to be greater than m. F of x is greater than m. This is the official, it's not really delta epsilon, it's the delta m. Although some people would say choose a specific number epsilon. Some people call this epsilon to maintain the delta epsilon flavor. I think that probably loses more than it gains. And so this is the official delta M representation of this notion. There are a few others that we could play with, but this gets the idea. I won't have you work through this. I'm not going to have you, I'm not going to have you verify this like we did with the delta epsilon intervals in the finite realm. But this is the idea of what's happening here. And it says that no matter how high we pick, if you get close enough, the function values get above that value in question.